A group of students prepare a large batch of conductive dough, a soft substance that can conduct electricity, and then mold the dough into several cylinders with various cross-sectional areas A and lengths L. Each student applies a potential difference, delta V, across the ends of a dough cylinder and determines the resistance of the cylinder. The results of their experiments are shown in the table below. So what they're doing, they're taking this material, this conductive dough, and they're making cylinders of different cross-sectional areas and different lengths. So they're varying the area, the cross-sectional area and the length, but it's all being made out of this the same material. And then depending on how they vary that, you get different resistances. The students want to determine the resistivity of the dough cylinders. So just as a reminder, resistivity is different than resistance. A particular shape of a given material will have and length and cross-sectional area, all of that will have a given resistance. But a resistivity is a property of the material. And the relationship between resistance and resistivity, you could write it as resistance is equal to resistivity, which is usually represented with the Greek letter rho, times the length of the thing that you're measuring the resistance of, divided by the cross-sectional area. And so if you have a higher resistivity, all else equal, that would make a higher resistance. But if you have a higher length, that also makes a higher resistance. But if you have a higher cross-sectional area, then that lowers the resistance. And if you were to solve for rho, you could write rho is equal to resistance times cross-sectional area over L. So it then says, indicate below which quantities could be graphed to determine a value for the resistivity of the dough cylinders. You may use the remaining columns in the table above as needed to record any quantities, including units, that are not already in the table. So pause this video and think about how you would do that. Well, I can think of two ways to do that. You could make a plot, you could make a scatter plot, where on the horizontal axis you put L over A, and on the vertical axis you put resistance. And then the resistivity would be the slope of a line that you try to fit to those points. So that's one way to do it. Another way to do it is you could make your horizontal axis your A over L, and then you can make your vertical axis your rho, and then you could try to fit a horizontal line to those points because your resistivity should not be dependent on A divided by L. I'm actually going to pick this second option because if I'm doing this primarily by hand, it's, at least to me, easier to fit a horizontal line than to fit a non-horizontal line, as I would have to do there. So let's do that. So my vertical axis, I'm going to do resistivity. So that's resistivity. And it's going to be in ohm meters. And then in my horizontal axis, I am going to do my area divided by length. And that's going to be in meters. And now, to be able to do this, I need to calculate these things. So I want to calculate my area divided by length. And I also want to calculate my resistivity, rho. And so area divided by length, 0.00049 divided by 0.03 is equal to 0.016. So we have 0.016, two significant digits here, two significant digits in the things that I'm dividing with. And then I can calculate rho by multiplying my area divided by length times resistance, times my resistance that I measured, 23.6. It's important to realize that when you do things experimentally, things aren't going to be perfect. There's a lot of noise in the real world. So I'll round that to, since I have two significant digits here, two significant digits here, so 0.39. So this is 0.39. And then I'll keep doing that calculation. And for the sake of time, I will just speed up the video now. All right, and now we can move to this second part now. It says, on the grid below, Plot the appropriate quantities to determine the resistivity of the dough cylinders. Clearly scale and label all axes, including units as appropriate. So as we mentioned, on our horizontal axis right over here, we want to put our cross-sectional area divided by the length of our resistors. And so that's going to be, we have meter squared divided by meter, so that's going to be in meters. And then in our vertical axis, we want to plot our resistivity rho, and that's going to be in ohm meters. And now we need to think about the scales. And so the scale of this vertical axis, if we go back over here, we see that all of our calculations for rho, well, it's between around 3/10, 4/10, like that, or you could say between 30 hundredths, and I guess we got up to 41 hundredths. So we could have a reasonable scale here. We have 1, 2, 3, 4, 5. So we could say this is 10 hundredths, which is the same thing as 1/10. This is 20 hundredths. This is 30 hundredths. And this is 40 hundredths for our rho scale. And then for our area divided by length, we have, so let's see, if we view all of this in terms of 10 thousandths, we go between 38 10 thousandths all the way to 160 10 thousandths. So let's make this 50 10 thousandths, 0.0050. This would be 100 10 thousandths, 0.0100. This would be 150 10 thousandths, 0.0150. And this would be 200 10 thousandths, 0.0200. And this would be 250 10 thousandths. All right, I think I have my scales right. So now we just plot our points. So let's see, the first one has a resistivity of 0.39, and our A divided by L is, this is going to be in meters. This is going to be 160 10 thousandths of a meter. And so we would go look up 160 right over here. So this is 150. And then we'd want to go 1/5 of the way between this, and it's neatly divided into 5 sections here. So this would be 160, and then I would want 0.39 ohm meters for the resistivity. So that would put us right over there. So that's my first data point. And now if I go to my second one, 98 10 thousandths, 0.31. So 98 10 thousandths will be right around here. And then at 0.31 would be right around there. So that's my second data point. And then I get to 66 10 thousandths and 0.41. So 66 10 thousandths would get us, let's see, this would be 66 10 thousandths. And then we have 0.41. So that puts us right over there, someplace like that. And then last but not least, 38 10 thousandths and 0.4. So then we have 38 10 thousandths. So this would be 40, this would be 30, so 38 is like here. And then we go to 40 hundredths, so it is like that. So those are our 4 data points. And then they say, use the above graph to estimate a value for the resistivity of the dough cylinders. Well, as we said, the resistivity should be constant. It shouldn't depend on our area divided by our length. And so if we want to fit a horizontal line to this that gets as close as possible, ideally we would have a computer, but we're going to hand do it. We have 3 of these points that are pretty close to 40 hundredths, but then we have this one down here. So I'd want to get a little bit closer to these 3 up there because there's so many data points there. So I would say a line that looks something like that. And so this point right over here, this is maybe approximately 0.37. So this is 0.37 ohm meters. I would say 0.37 ohm meters. And we're done. And frankly, another way to think about this is you could have done it potentially even without the graph by saying, well, look, a good estimate for my resistivity of my conductive dough is to just take the mean of these values. But they wanted us to use a graph, and so one technique would be, all right, let's try to fit a horizontal line. The other technique with the graph would have been plotting L over A here, and then plotting resistance on our vertical axis, and then our estimate of the slope of the fitted line, that would be our estimate of rho. But that would have been, frankly, harder to do than even what we did here.